Okay everyone, so in this video we're going to go ahead and we're going to talk about another data structure that's kind of the complementary data structure to stacks, and that is the queue data structure. Okay, so again, just like a stack, a queue is another way that we apply rules to how we access certain sets of data. Okay, whereas a stack was first in, last out, a queue performs the first in, first out behavior. Okay, so the first thing to get in line is going to be the first thing to get out of line. Whereas, we could compare a stack to, the stack of plates at a buffet. Queue is the same as something you would see in, movie ticket lines. Or waiting to get seating at a restaurant, right? When you walk up to a restaurant and you say, I have a party of 4, you have to wait for all of the people that got there before you to be seated before you get seated, right? So that's the general idea behind a queue data structure, right? The newest thing is going to wait the longest amount of time to get out, whereas in a stack, the newest thing was the first thing to come out. Right? And just like stacks, queues play a very large and pivotal role in our computing architectures today. You won't necessarily get into any of that until you take something like an operating systems class or stuff like that. But they do have roles to play, our with our computers and launching applications. There's lots of different applications running on our computer at the same time, and they're all trying to get processor time so they can actually run. And then queues are used to judge, okay, what is the next thing to actually be run by our computer, right? So just like stacks, this is another very large data structure to know and understand. Okay, so whereas with stacks, we were only caring about what the top element was, in queues, we are now caring about what the front element of the stack is. So basically, who got there first, right? We also need to effectively find out where the back of the queue is, but we're not going to necessarily worry about what's at the back. We just need to know where the back of the queue is so we can add new elements to the back of the queue. And also, like stacks, we can implement a queue using many different structures, whether that be an array or a linked list. However, personally, I would say that it makes more sense to use a linked list for a queue than an array, just because of the way we're going to be shuffling things back and forth, which might become, rather confusing with an array. Just because we're looking at things from both ends, right? We need to remove from the front and add to the back, whereas with a stack, we were both adding and removing from the first element. Now we're looking at the first and last element, which makes using it in an array a little funny sometimes. Okay, so just like a stack, there are some well-defined functions and naming schemes that we should and will use when we're talking about queues. Basically, we have the enqueue function where we put something into the queue. We have the dequeue function where we take something out. We have the front function where that accesses whoever is next in line to get out of the queue, or who is the first in front of the queue, in front of the line right now. And we also have the isEmpty function to check to see if our queue is actually empty. Again, we will only ever access the very first element in the queue. We're not necessarily going to have any need to see who's in the middle of the queue or things like that. We may have functions just for our personal selves that print out the entire queue just to make sure things are being put in there in the correct order, but that's not necessarily a well-defined queue function. Other than that, let's just kind of take a look at our queue. I should have probably written on here when I did this what's the front and what's the back, but I didn't. So we're going to say the left side is the front and the right side is the back. Oh, goodness. Uh-oh, PowerPoint froze. Okay, anyways, just remember left side's front, right side's back. Okay, so we NQ1, which we have 1 put into the queue. After that, we NQ20, and remember this is a queue, right? So our number to the leftmost is the front, the number to the rightmost is the back. Alright, so 1 is our front of our queue and 20 is our back of our queue currently. If we NQ40, 40 gets put behind 20 because that is just the ordering we will follow. 10 came after 40, and then after that we go ahead and we call front. And of course 1 is the front of our queue. After that we would call DQ, which removes 1 from the queue, and now 20, which was directly behind 1, becomes the new front of the queue. After that we can call front, which would print out 20. We could call DQ again, which removes 20 from the queue, making 40 the new front and 10 still the back as it has been. After that we could call NQ again, which would just shove the new number on the back of the queue. NQ22, which would do the same thing. And it would just continue in that pattern over and over again until we had finished doing whatever our ultimate goal was for that queue. Okay, if we are using linked lists to represent our queue, we have to again ask ourselves some basic questions, and that we asked, similarly to how we built our stack. The biggest one being, how do we link everything together? Right? Do we have a front that is pointing to the front of the queue, which points to the next element, which points to the next element, or do we reverse that all and have the back element basically pointing towards the front? Right? And this is going to basically determine how things are going to work out for you in the long run. Personally, I would definitely suggest this first one here. Otherwise, you have to do some goofy walking and traversals to make everything work correctly. At least in my head, right? Everyone has a little bit different way of thinking about this stuff. Okay, so if we were going to build just a queue representation of a linked list, we'd basically start off with something like this. We would have a front pointer pointing at null because there's nothing in the list. After that, we could go ahead and NQ1, in which case 1 or front would point at 1, and then we would basically be done, right? Because that's all there is in the queue. After that, we could NQ2, which we would tack 2 onto the back of the queue, and we would just keep going. We would tack 3 on for NQ3, tack 4 on for NQ4, even though apparently I still typed 3 there. Just pretend that's a 4. And then after that, we could go ahead and actually DQ the front of the queue. If we would do that, all we need to do is move the front pointer to point at the next front element, and then we just remove the old, right? So we move our front pointer and remove the old element. We do the same for each element that we try to remove. Alright, so this is just the same known behavior that we've been talking about, the whole time. Right, so just as our stack operations should have looked very familiar, our queue operations should also look very familiar. Remember, a stack push was effectively a list prepend, and a stack pop was effectively a front remove. Okay, the same basic things are going to apply here. Right, so an NQ is still effectively a remove front, and a DQ, on the other hand, is a list append, where we append the new node on back of the list, right? Okay. If we look at just our actions that are happening here, add to the back, add to the back, add to the back of the list, remove the front, add to the back, add to the back, right? We're just doing the same operations over and over again. The one thing we can kind of note here is that a list append is going to force us to find the end of the queue or end of the list each time we run it, right? And that could potentially be a little time consuming. Right? So if we NQ34, or if we wanted to NQ34, we would effectively start at the front, and we would traverse the list until we found a pointer that was pointing at null, right? Because that says this is the end of the list. Then we would go ahead and add our new number there. Okay, and if we had a really big queue with lots of things in it, that could potentially get rather time consuming, especially if we need to do that multiple times in a row. All right, so what's one possible way that we could go about and making this a little more efficient? And the easiest way is basically, hey, why don't we add another pointer? So now we would have a pointer pointing at both the front of the list and the back of the list. Okay, so now we effectively no longer have to traverse the entire list over and over again whenever we need to add something to the back. Right? All we need to do is just go directly to the back pointer, add it on there, and then move our back pointer to point at the new back of the queue. Okay, this does add a little more work for us, however, because now we need to make sure that the back pointer is always updated and in the correct position. Because if it's not, we could run into quite a few problems. Okay, this is going to be kind of a trade-off thing that we're going to see over and over again as we look at many other data structures. And we're going to basically be looking at a trade-off of having a very simple data structure that doesn't necessarily take up a whole lot of memory, but could have some rather slow operations. Right? So before we used two pointers, all we had was basically a front pointer and then the data itself. Right? But as we noted, enqueue functions could be rather slow on large data sets, right? Because we might have a queue with 1,000,000 items in it. However, we can use sometimes more memory space and add a little more complexity, but by doing that, we decrease the overall time that our function takes. So we increase the complexity somewhat, but we also then may increase the overall efficiency of the algorithm as a whole, right? By adding the second back pointer, we add more complexity to our data structure, but or I should say we add more complexity and it requires more memory space, but we dramatically increase the efficiency of our algorithm now, right? So this whole trade-off is basically a time, how much memory space does our program take and how complex is it, versus space, or time versus space trade-off, right? And we're going to see this trade-off or I should say many times over and over again, right? Time where we might have a simple but slow algorithm, or a complex, rather large algorithm that runs much faster, right? So often, more times than not, we as programmers are trying to find this middle ground between the whole time versus space trade-offs that we will see. But we will definitely get more into that later on. Okay, so if we want to look at our same few number sets here, but now with a front and a back pointer, we will see that things are going to get much easier. Right now, if we want to enqueue35, all we need to do, instead of traversing from here to here to here to find out where to put that node, we just need to jump directly to what the back pointer is pointing at and tack our new node on there. Right? After we've tacked the new node on, we update what back is pointing at to make sure it's in the correct state for our next function. Right? If we enqueue4, again, we do the exact same thing. We just go to the node that back is pointing to, and then tack our new element on there. And then after we're done, we update the back pointer. Right? So this is why it's important that the back pointer must be kept in a good state at all times. Because if it's, if we forget to basically increment our back pointer to this new node, it could cause issues whenever we enqueue something. Okay, so that is basically queues in a nutshell. If you have any questions, make sure you get a hold of me. Definitely look at your next assignment, as it basically has mostly to do with queues. So check that out and let me know if you have any questions. We'll see you in the next video.